Right, so today we're going to start looking at what's called radical functions. Anybody know what I mean when I say radical? Another word that sometimes we use for radicals. not groups that not groups of people, but yeah, roots. Yeah, so we're going to talk about different kinds of roots, whether it's square roots or cube roots. In general, we're going to see a pattern that when you graph even roots, okay, those all pretty much look a certain way, and so do odd roots. Okay, so these are both examples of radical functions. One on the left is pretty straightforward. It's a square root function. It's been shifted 2 units in one direction. And we are going to talk about transformations as well. Okay, exactly the same rules as what we did with parabolas in every other function. Does anyone think they know which way this has been shifted? The square root x minus 2? It's been shifted 2 units to the right. Yeah, that's correct. All right, so when you add or subtract a number inside the function, that's your horizontal shift. And then if you add or subtract a number outside, that's your vertical shift. Okay, so anything that's of this form, okay, where you have that root symbol and the index, as long as it's a number that's greater than 1 and an integer, okay, that's called a radical. So the index is the number that's written inside that, well, it's like in that little check mark part of the root. Okay, and that just tells you what kind of root it is. If you don't put a number there, it's automatically assumed it's a square root. Okay, it's a 2. Okay, so n is called the index. How about the number under the root? Does anyone know what that's called? It begins with an R. It's the radicand. Yep. So we got to be careful with certain kinds of roots. There's restrictions on the radicand, like think of square roots. If you're dealing with real numbers, you can only take the square roots of certain radicands. Okay? And for square roots, it's positive. When you get into cube roots, okay, we have a little bit more flexibility. You can take cube roots of positives or negatives, and you don't get imaginaries. All right. Okay, and then the symbol itself, that's the symbol that you always use for any kind of root. Okay, so any questions on those basic terms? Radical symbol, index, radicand. All right. So as I already said, if there's no index, you always assume it's 2. Okay, that's like your square root symbol. And another way you can write a square root, a cube root, fifth root, is instead of writing the actual symbol, you can write it as an exponent. Okay, so for example, if you want to take a square root of something, it's the same as raising it to the 1/2 power. Okay, it's exactly the same thing. And why you might want to write something with an exponent rather than the root symbol is because it allows us to simplify certain expressions. All right, so just I'll show you an example. I'll take the square root of 9, and then I'll raise 9 to the 1/2 power, and you'll see it comes out the same. So square root of 9 gives me 3, and 9 you can do to the 0.5 or 1/2, same thing, and you get 3. Okay, so any thoughts for a cube root, what the power would be you could raise it to and get the same answer? Yeah, Amanda?
Would it be 1/3?
Yeah, it's basically 1 over the index. Okay, so if you want to take the cube root of something, you could raise it to the 1/3 power. How about if you wanted to do the 5th root of something? Bless you. Yeah?
1/5.
1/5. And this is a good example, bless you, because you have a power when you change it of 1/5, but you also had a power of x to the 4th. So this is something you can simplify. Does anybody remember what you do with your exponents when you have a power to a power? You add them if you're multiplying like x squared times x cubed. You add the 2 and the 3, and that'd be x to the 5th. But you don't add the exponents in this case. Anybody remember what you do? Like if I said to do like, let's say 2 cubed, and I said raise that to the 4th. What does that mean to do? Like take 2 cubed and do what with it? What does that mean to do? No, just like pretend I don't want to write this 4. How would you write out 2 cubed to the 4th the long way? Like say they don't understand this extra exponent.
Wouldn't you do 2 times 2 times 2 and then 4 times?
Okay, so I see what you're saying. What's another way you could write it? A little bit shorter, still having an exponent in it, but just not having 2 exponents.
Would it be 2 to the 12th?
And how would you get that? How would you write that out so someone could see where 2 to the 12th is coming from?
Would it be 2 to the 3rd times 2 to the 3rd?
Yeah. So you could write it out. The 4th power means take what's inside here, multiply it 4 times. So it's 2 cubed times itself 4 times. And now you can use the rule David said, that's when you add the exponents. 3 plus 3 plus 3 plus 3. So we get 2 to the 12th. So what's the shortcut you can really do now that you can see where it comes from?
Just multiply the exponent.
Yeah. When you have a power to a power, you multiply your exponents. So what's x to the 4th to the 1/5? Yeah, Tom?
X to the 4/5.
Yeah, x to the 4/5. All right, so that's why you might write something as an exponent rather than as a root, because it just allows you to simplify it using your properties of exponents. All right, so now we're going to talk a little bit about solving equations. Now, if they ask you for what's called the principal root, that means they only want one answer. Okay, remember, if you're solving equations with a root symbol and you're considering reals and imaginaries, there's always as many answers as the index. Okay, so if you're doing a square root problem, there's 2 answers. Okay, if you were doing a cube root problem, there's 3 answers. Some might be real, some might be imaginary. But what they might ask you on the test or in homework is just to find the principal root, which means they just want a single answer. Okay, and this is how you do it. Okay, if your index is odd, you're going to find the real solution basically to this equation, x to the n equals a. Okay, let me show you an example. Let's say we had something like x cubed equals 64. Okay. If I asked you to solve something like this, it's going to turn into that when you solve it. Okay. What you'd end up doing is taking the cube root of each side, and you get x equals the cube root of 64, okay, which would be how much? 4. Okay. 4 times 4 times 4 is 64. And that would be the only answer to this problem you would write if I ask you for the principal root. Let's see. All right, so when you have an equation with an odd root, you just take, with an odd exponent, just take that root of each side. So it's a 5th exponent, take a 5th root. If it's a 13th exponent, take a 13th root. Okay, whatever you have to do on both sides. Now, if n is even, here we got to be careful because you get 2 answers. Right? So if I said find the square root of 4, 2 is an answer, because 2 times 2 is 4, and negative 2 is also an answer. But if I say find the principal root, okay, what that means is I want the answer that's not negative. Okay, so in that case, if I said what's the square root of 4, the only answer I would want is 2. Okay, so you're finding the solution that is not negative. And solving equations that have roots, it's not too bad. Okay, if you just had something like, we'll go a little more complicated than just numbers, but if you had something like this, it's not too bad. All you really have to do is square both sides, and you end up with something like this. And then you get x equals 146. Okay, where it starts to get a little harder is when you have multiple square roots in the problem. Like if I did something like this. Now that's a little harder to do. Because when you square things, you can't square terms. It's not like you can just square the first term, the second term, and the third term. It doesn't work that way. When you square something in an equation, you have to square the entire side, which leads to lots of foiling. All right, so we'll look at some examples later on that have multiple roots in them. All right, so now I want to just look at some patterns and see when you take square roots, what ends up happening. So if you take the square root of 4, what do you get? 2. So did it get smaller or did it get larger? Okay, so in that case, I took the square root, it got smaller. Okay, square root of 18, 4.24. Did it get smaller or larger? Smaller. How about the square root of 1? So what happened there? It stayed the same. So it didn't get smaller. How about the square root of 0.5? What do you think is going to happen there? So you're trying to think of two numbers you multiply together that give you 0.5. So could you have two numbers you multiply together that are smaller than 0.5? And when you multiply them, you get 0.5? What do you think? Take a number smaller than 0.5 times a number smaller than 0.5. Would you get 0.5? No. So if you take the square root of 0.5, you need to multiply two numbers that are bigger than 0.5 together to get 0.5. So if you want to multiply two numbers together that are the same and you get 0.5, it's 0.71. So 0.71 times 0.71 is 0.5. What happened that time?
Got bigger.
Yeah, this time it got bigger. And same thing's going to happen here. If you want to multiply two numbers together and get 0.2, and they're the same, the numbers have to be bigger than 0.2.
Why is that?
Why is that? Well, let's think what happens if it wasn't. Take a number less than 0.5 times a number less than 0.5, and they're the same number. If you multiply two things that are less than a half, would you ever get a half? It's got to be bigger. You've got to multiply two things that are bigger than a half, if they're the same. So that's going to lead to something kind of interesting when you graph it too. Okay, you're going to get kind of a certain behavior after 1 and a different behavior before 1. All right. So point here is you're just going to be careful when you're taking square roots, whether they get smaller or larger. All right, these I'm going to graph, and we'll start to look at some patterns. So I'll graph square root of x. Now to type in the 4th and the 6th root, start with the index, go to math, and then the 5th option down. Okay, so that's your 4th root of x. And then to do the 6th root, type in the index, math, 5th option again. So I'll start with a standard window, but then I'm going to have to zoom in to kind of see the behavior a little better. Okay, and what I'll do is let me underline these in the colors they are. So I think I did blue, red, and then black. So that one was blue, red, black. All All right, so that's your standard window. What do you notice about all these functions? What's something they pretty much all have in common? Yeah?
They're in the first quadrant.
Yeah, they're all in the first quadrant. None of them extend into negative x values. Okay? So that's something that happens with these kind of indices, even indices. Odd is totally different. Okay? But even indices, pretty much always in the first quadrant. What I'm going to do now is, let's focus on just the first quadrant then. So let's take this section and make that bigger. So let's set our x min at 0 and y min at 0. It's good to start with the big picture, just in case it was over in the other quadrants, but we know it's not. So now we'll focus just on quadrant 1. Okay, and now I kind of want to focus on which function is above the other. It's still a little hard to see. But anybody think they can kind of see what's happening near 1? Yeah?
One, they're all intersecting each other.
Yeah.
One.
They're all crossing right in that point 1, 1. Because if you take the square root of 1, the fourth root of 1, or the sixth root of 1, you get 1. So that's a common point to all of them. Let's zoom in just on that section and see if we can start to see something a little more. So let's just zoom in. Let's try to get kind of close to that intersection point. Now you should be able to see what I'm looking for pretty clearly. Can anyone describe what's happening there in terms of which function is on top of the other? Molly?
Like the one that you see on top, like after they intersect, it goes to the bottom, and then the bottom one goes up to the top.
Yeah, and this has to do with that behavior of whether you take square roots and cube roots, whether they get smaller or larger. So what happens is that before 1, the blue one, okay, which was the square root, that was the smallest. And then all of a sudden, if you go after 1, square root becomes larger. So in other words, if you were to compare the square root and the fourth root of a number bigger than 1, the square root is always larger. If you were to compare the square root and the fourth root of a number before 1, okay, the square root is always smaller. All right, so they all kind of switch their positions after 1. All right, so now I'll just kind of summarize some of that in writing. All right. So 0, 0, that's a point that all the graphs go through. And 1, 1. Okay, that's another point that they all go through. Okay, by looking at the big picture, we could see the domain and range. Okay, domain, we can't go into the negatives. Okay, we don't take roots with even indices, do not have radicands that are negative. If you did, you'd be getting into imaginaries, okay, which we're not doing in this section. All right, so domain is any number from 0 to infinity, and range is also 0 to infinity. Okay, another way to say that, you're in quadrant 1 all the time. Or on an axis. 0, 0, technically that's not in quadrant 1. Okay, and here's the pattern that we looked at visually, just summarized as an inequality. If you look at numbers between 0 and 1, and you take a square root is always the smallest. Fourth root would be a little bigger. Sixth root would be a little bigger. Eighth root, even bigger. Okay, 10th root, even bigger than that. So between 0 and 1, the bigger your index, the bigger the result. That switches when you get bigger than 1. For numbers bigger than 1, the bigger your index, the smaller your result. So a 10th root is going to be a lot smaller than a fourth root. Right, so just summarizing the picture as an inequality. Okay, so any questions on kind of the general properties of roots that have even indices? All right, so now we're going to look at odd indices. So just as an example before we start, what's the cube root of 8? 2. What about the cube root of negative 8?
2.
So 2 times 2 times 2 is still positive 8. But what times what is negative 8? Negative 2. Negative 2 times negative 2 times negative 2, that's negative 8. So that's a huge difference right away. You can take the cube root of a negative, which means this time the domain, it's not going to be just going in the positive x values. It's also, there's going to be an image when we go to the left. So let's graph cube roots and fifth roots and just see what they look like. All right, so what I'll do is just change that to a cube root and fifth root. Okay, so I'll graph the cube root in red and fifth root in black. Red, black. Okay, and what I'll do is I'll put the pictures up here. Okay, let's do standard window to start. Okay, so there's the cube root. And there's the fifth root. Okay, so first thing you should notice is it does go in both directions. Does anybody think they see a point that's common to both of those?
0, 0.
Yep, 0, 0 is a point that's common to them. There's actually 2 other points. Yep.
1, 1, negative 1.
Yep, 1, 1. And negative 1 is a point that's common to all of them. So anytime they have a point that's in common, that's where you're going to kind of get the behavior switching, which one is on top. So cube root functions switch kind of which one's on top and bottom a lot more. So let's just take and zoom in on that section and kind of see what's going on in a little more detail. Okay, so what I'm going to do is let's just set the window like -3 to 3 on everything. And if that's not enough, we'll zoom in more. All right, so let's, I think I'm going to set the Ymax to a -2. So then I can just kind of stretch it out a little more. Might make it just a little clearer to see. So it's getting pretty vertical in that middle section. That's why the calculator is having a little trouble sketching it. All right, so let's take that. And oh, it's not going to let me grab it. So let's just look at it like that. So when does it look like the black function is underneath the red one? Can you be more specific about when what do you mean when it's negative? Because I can see the black function is on top of the red one, even in some of the negatives. Between -1 and what? And 0. Yeah, between -1 and 0, the black function is below. And if you go from 1 on to infinity, the black function is below. And the red one is on top in the other cases. Okay, if you go from 1 to infinity, okay, the red one is on top. And then between -1 and 0, the red one is on top. Now the other two places we can look is what's happening between 0 and 1, and what's happening from -1 back to -infinity. The behavior is the same in both of those sections. Between 0 and 1, the black one's on top. Between -1 all the way back to -infinity, the black one's on top. Okay, so what ends up happening here is they switch places a couple different times, and I just can't grab that picture, but that's the picture. Okay, so this time the functions go left and right forever, and up and down forever. Okay, so domain is basically all real numbers. And the range, all real numbers. Okay. Now, in general, I'm not going to ask you on a test like, would the cube root or the fifth root be greater or smaller? I just kind of want you to understand that they switch places depending on the interval. Okay, so in general, if you're dealing with numbers that are less than -1 or between 0 and 1, as the index gets bigger, your answer gets bigger. As long as you're dealing with numbers between what I just said. So a fifth root would be bigger than a cube root. A ninth root would be bigger than a seventh root. Now, if you want to deal with numbers that are between -1 and 0, or numbers that are greater than 1, as the index gets bigger, your answer gets smaller. So in that kind of problem, a fifth root would be smaller than a cube root if you're between these numbers. Okay, so they're kind of complicated. There's a lot of different things happening here. Okay, but what's nice now is we have a general picture of what odd roots look like. Okay, odd roots pretty much always have this kind of horizontal S shape, and even roots always pretty much have this curve that can start at the origin if you don't shift it, and then just curve up very slowly. But that's the general shape of even roots and odd roots. All right, so now we'll take a look at the transformations. Okay, so what I've done is I've written kind of a generic problem. It doesn't matter what the index is. Whether you're doing a cube root or a square root, these two problems would be the exact same transformations. They look different, but if you compare the first one to just the basic x cubed and you compare the second one to just the basic square root, both of those are just transformations 2 units to the left of their basic functions. All right, so A is a shift left and right. It's your horizontal shift. Okay, if you want to write that in, you can, but we've done it before, so I'm not going to put that in. So that's your horizontal shift. What about B? What does that do to the graph? Yeah?
Wouldn't it make it wider and thinner?
Which way? Horizontal or vertical? Nope, that's going to be C. C is going to be our vertical stretching. So B is your horizontal stretch. This is all horizontal stuff. Anything that's inside the function or under the root, it's your horizontal shift left and right, horizontal stretch. What you have to be careful with A and B is they do the opposite of what you would expect. So if you see a +2, you think, oh, positive numbers go to the right. Well, on a number line they do, but the shift is actually to the left. So a +2 shifts to the left. Same thing with B. You might think, oh, bigger number is going to stretch it bigger. No. When B is a big number, it actually compresses it. When B is a small number, it stretches it. So if you put in a number like 0.5 for B, small number, would actually make it bigger. Okay, so everything that I just circled is kind of the opposite of what you would expect. C and D are not. They're exactly what you would expect. Okay, so C, I already said, that's a vertical stretch. Bigger number for C stretches your graph vertically bigger. Smaller number for C compresses it. And the last shift is D. What does D do? Yeah, it's going to shift up and down, and it's exactly what you would expect. Positive numbers shift up, negative numbers shift down. If either B or C is a negative, okay, what would that do? When you put a negative in, that causes the graph to do what? Like compare, like if you were to graph like x squared versus negative x squared, they would be what of each other? Yeah, it'd be a mirror image. All right. So negative in front of B causes a reflection. Negative in front of C also causes a reflection. Negative in front of B, that's a horizontal reflection, because that's the horizontal stuff. Negative in front of C, that's a vertical reflection, because C is the vertical stretch. All right? So the most number of transformations you could have in a problem are 6. Okay? You could have an A, a B that's negative, a C that's negative, and a D. That would be 6 separate things to list. Right, so we'll look at just some basic ones, and we'll see if we can figure out the transformations. All right, so let's start with square root of x minus 2. Okay, you're going to compare that to the square root. Okay, you always just compare it to the basic one if it didn't have any numbers for A, B, C, and D other than a 1. Or a 0 in case of vertical stretch or horizontal shift. All right, so how would you sketch g of x if you had the graph of square root of x? What would you have to do with the square root of x? Well, Josh?
Shift it to the right 2 units.
Yeah, we shifted to the right 2 units. So explain how to sketch g of x. Just write to sketch g of x. Okay. Take square root of x and shift right 2 units. Okay, that's basic one. This is only one transformation. How about h of x? What would I do to the square root of x to get h of x? Yeah?
Could we move it to the left 3 units?
Yeah, this one, again, it's the opposite of what you would think, so this would shift left 3 units. So take square root of x and shift left 3 units. Okay, now the next one's a little tricky. Why is k of x a little tricky? What's different about it compared to g of x and h of x? Yep.
The 3 is in the front.
Right. You don't want it like this. This is not the order that it should be in when you're looking at transformations. Okay. It should always be exactly like I have it up above. Right. So can you tell me, Amanda, how I could rewrite this?
The negative x plus 3.
Can you say it one more time?
Negative x plus 3.
Perfect. Yep. Now that I've done that, I can see that there are 2 transformations that are happening here. Right, so I'm just going to write down to sketch k of x. Take the square root of x. And what would you do first? Well, Molly, do you have any thoughts? What would you do first to sketch k of x?
Go left 3 units.
Yeah, you take this basic function and shift it left 3. So take square root of x and shift left 3. And what about that negative in front of the x? What's that going to cause to happen? Yeah, it's going to be a horizontal reflection, which means reflect it over the, if you're reflecting horizontally, okay, that's going to reflect over the y-axis. Okay, so take the square root of x and shift it left 3 and reflect over y-axis. So that would cause a big change in the domain if I asked you about that. So now instead of having a graph that would look something like this, it's going to look like that. Okay, so now your domain is going to be in the negative numbers. Okay? Which should make sense, because if you try plugging in positive numbers for x, and you're going to run into a problem now. Like positive 10, put a negative in front, now it's negative 10 plus 3. I can't take the square root of negative 7. But if I plug in negative 10 for x, the negative in front of the x and the negative with my 10 cancel, and then I get 10 plus 3 is 13. And that I can do. Right, so you can reflect your square root into any function you want, any quadrant, just by putting a negative in front of the entire function or a negative in front of the x. Okay, so any questions on the transformations? All right. So anytime you want to sketch a function, always start by sketching the point that would have been at the origin. Okay, for an even root, I call that the start point. Because even roots always start at the origin and then go in one direction. For an odd root, 0, 0 is not the start point. It's more of the center point. Okay, that's in general what your odd roots look like. Okay, but regardless if you're sketching an even root or an odd root, always make sure that you sketch 0, 0. Okay, kind of gives you the basis where to start from. So how do we figure out the 0, 0 point if we shift it and stretch it and flip it and all this stuff? Well, to get the x value, all you have to do is take the radicand and set it equal to 0. Right, so you get your radicand, set it equal to 0. That's the x value. To get the y value, well, if you've got the x value, all you have to do is plug it in. Okay, you're going to have a formula, and if you know the x value, say, comes out to, I don't know, 2, then all you do is plug 2 in for x and solve for y. Okay? And that'll give you your y value. So that's just using substitution. Okay, and then once you have your start point or your center point, depending on if it's an even or an odd root, graph other points to get the idea of the curve. Now, why do I say pick points to the left and the right, and then I put if applicable? Why wouldn't it always be applicable to check points on the left and the right of 0, 0? Right, and if you're doing even roots, it's only going to go in one direction. So you only need to check points. It could be to the left or it could be just to the right. Depends if you reflected it. But when you're doing odd roots, always check points on both sides. Right, so first what I'm going to check, or I'm going to sketch is a cube root function. Okay. Do cube root functions just go in one direction, or do they go in both directions? Yeah? Both directions. Okay. So I'm going to try to figure out what's happening here. I'm not asking you for the transformations. Okay, I just want to sketch. But if I was asking for the transformations, this would be my first step. And there's 5 transformations happening here. Okay, I'll just say them just to make sure we know what they are. You're shifting left 3. You're doing a horizontal compression by a factor of 2. You're doing a horizontal reflection, vertical stretch by a factor of 2, and you're shifting up 1. Okay, those are your transformations. All right, now we're going to sketch it. All right, so it says set the to get the x value, set the radicand equal to 0. Okay, if I do that, what do I get for my x value? Yeah, Amanda?
3 over -2.
Careful, when you move that 3 to the other side, it would also become negative.
So it would be -3/2. Or would it be
3 halves, right? If you plug in 3 halves for x, you would get -3 plus 3, which would be 0. Okay, so x is -3 halves. And now I want to know my y value. So if I plug in -3 halves for x and then add 3, well, I already know what the radicand comes out to. 0. Okay, because I picked -3 halves to force this to be 0. So now what's the cube root of 0? 0 times 2, and then plus 1. All right, so this graph is going to have a point on it of -3 halves, comma 1. And that's going to be kind of the center point of this cubic function. And now I'm going to check points to the right of it, and I'm also going to check points to the left. Okay, and that's where the graphing calculator is helpful, because the table can check points fast. So let's just get a grid. Okay, I'm going to start with -1.51. And the first question I asked is, does this graph go in both directions? So that tells me that I should be checking x values that are above 3 halves and, above -3 halves and below. All right, just to get an idea of the curve. All right, so let's type in our root. 2 times the cube root of 3 minus 2x. All right, so we got 2. And you have to put in the time symbol, because if you don't, what's going to happen is if you just put a 3 next to it and now go to type in your root, it's going to take the 23rd root. All right, so you've got to put in 2 times. Now I can put in cube root of 3 minus 2x plus 1. Minus 2x, and just make sure the plus 1 is on the outside. Okay, I'm just going to check the -1.51 just to make sure we did that right. Let me make sure I typed everything right.
So isn't it supposed to be just 1.5 -1.5?
Yes, that's right. Thank you. I think I had said that, and then I didn't write that. So now let me check 1.5. Perfect. Okay, so 1.5 comma 1. That's a point. And now I'm going to fix it on my graph. Right, let's check. Let's check 4, and then I'll check 8 and 10. I'll just check a few points. And try to hit enter between each one if you can. 4, 8, 10. All right, so 4, I'm at about -2.4. This is somewhere down here. 8, I'm at -3.7. 3.7. And 10, I'm at about -4.1. Okay, so I can start to kind of see the curve on that side. Let's get it on the other side. So we got 0, 3.8. All right, let's just do -5 and -10. It should be good enough. -5 is 5.7. And -10 and 6.7, roughly. All right. So now just connect that. Remember, it's that S-shaped curve. And that's it. Okay, there are no asymptotes here. This graph does not level off. The left side will keep going up very slowly, and the right side will also keep going down very slowly. Okay, let's check our graph and see how we did. Okay, notice the calculator puts a little break in here. It shouldn't have that, just because it's having trouble because it gets very steep in that section. Okay, any questions on that? All right, so that's sketching an odd root. Okay, does anybody want me to sketch an even root? You think we could do that one? Maybe let's just find the point that corresponds to 0, 0. Okay, how do I find the x value of the point that would have been at the origin, but it's not going to be anymore because I've shifted it? Amanda?
Would you do the radicand
Mm-hmm.
set equal to 0?
Set the radicand equal to 0. Okay, so the x value is going to be 4/3. Now, plug in 4/3 for x. You should already know what that's going to come out to. It comes out to 0. What's the 4th root of 0? 0 times 3? And then minus 2. Minus 2. So 4/3, comma, -2. That's a point on your graph. Now, am I going to end up checking numbers that go on both sides of 4/3 or just one side? Just one side, because this is an even root, right? You would have to pick numbers for x that do not cause what I circled to be negative. So what do you think that would be? Would you pick numbers bigger than 4/3 or smaller? What? All right, let's just try a huge number. Let's try 20. Okay, that's much bigger than 4/3. If you plug 20 in for x, what's 3 times 20? And what's 4 minus 60? That's a negative 56. So when you plug in numbers bigger than 4/3, you end up with negatives under the root. So we have to try numbers that are smaller. Okay, so I would graph this point, and then I would maybe graph 0, try 0, -5, -10, and you'll get a good curve. Okay? But any questions on how you would sketch it from here? Just try a few points in your table after you type in the function. All right, and remember, it doesn't go in both directions, just one direction. All right, so the last thing we'll look at is how we solve radical equations. Not too bad if you just have a single radical like this. Starts to get a little worse if you have more than one radical. Okay, so the goal, anytime you have a radical in your equation, you have to get it by itself and then raise each side to the power of the index. So if you have a problem with a cube root, you are going to cube each side. If you have a problem with a square root, you're going to square each side. And the number of times that you have to do that depends on how many radicals in the problem. Okay, I'm never going to give you a problem with more than 2 radicals. So you might have to square or cube each side up to 2 times. Anything more than that, it starts to get a little annoying. So we'll stick with up to 2 times. Like this problem. This problem has 2 radicals in it. You're going to have to isolate one of them and then do something, and then you're going to have to do it again a second time. Now, because of the method that we're using to solve these kinds of problems, you do have to check for extraneous answers. Now, when you're dealing with rational functions, the way you check for an extraneous answer is make sure you never divide by 0. Well, there's no denominators here, so you're not going to do a divide by 0. But what could be a problem with these kinds of roots, especially the kind I have in example 6? What could end up happening that you don't want? Yeah?
Square root is negative.
Right, because this is an even index root, so square root, we don't want to have any value for x that could make the radicand negative. So if you got negative 10 as an answer when you solve this, that doesn't work. Right, so I want to focus on solving it algebraically. Solving it graphically, I bet most people could probably do at this point. Just type what's on the left in y1, type what's on the right in y2, and see where they cross. But algebraically, it's a little harder. Okay, so what's it say the first step is when I'm solving a radical equation? What do I have to do first?
Isolate the radical inside.
I got to isolate one of the radicals. It doesn't matter which one. I'll get this one by itself. Okay, so how would I move negative square root 4x plus 9 to the other side? Yeah, we just add it. And now, raise each side to the power that was the index. Okay, there's no index written here. So what kind of root is that? It's a square root. So what am I going to do to both sides? I'm going to square them. Now, I'm not saying you square terms. You have to square the entire side. So that means you have to take this and square it, and this and square it, which ends up leading to FOIL, double distributive property. You cannot square the terms. You have to square the whole thing. Okay, this side's easy. We just get 6x plus 12. And now on the right side, what you're basically doing, if you want me to write it out the long way, is this. You're doing 1 plus square root 4x plus 9 squared. Okay, so we'll do it out. What's 1 times 1? 1. What's 1 times square root 4x plus 9? And then another 1 square root 4x plus 9. So how many of those do I have? So I have 2 of the square root 4x plus 9s. And what about square root 4x plus 9 times square root 4x plus 9? Right, it's like doing this. You're taking the square root of 4x plus 9 and multiplying it by itself. So you just get 4x plus 9. Okay, now at this step, we got to repeat everything we just did. Get the root by itself, and then square both sides again. So we've got some like terms I can combine. What do you get if you take 1 plus 9? You get 10. And what I'm going to do is I'm going to subtract 10 from both sides. So what I'm doing is canceling that out and moving it to the other side at the same time. So I get 6x plus 2 equals 2 square root 4x plus 9 plus 4x. All right, what could I do next? Yeah, bring the 4x over. So that's going to give me, that's gone. What's 6x minus 4x? So 2x plus 2 equals 2 square root 4x plus 9. Now I almost have the root by itself. There's one more thing I got to get rid of, and that's the 2 that's in front. Divide everything by 2. Now when you do division, that you can do to each individual term. Okay? That's how division works. So divide by 2, 2, and 2. So now we're left with x plus 1 equals square root 4x plus 9. So now at this point, we've got a much simpler equation than we had before. Okay, so we started out with something that had 2 roots. We isolated and squared, and now we just have 1 root. Okay, what am I going to do on both sides now? I'm going to square again. Square and square. But this time it's going to be a lot easier. So now x plus 1 squared, just FOIL that out. Remember, you're not squaring the terms. You have to FOIL. Okay. And what do I get on the other side? 4x plus 9. And now I'm basically down to what kind of equation? It's a quadratic. Okay, so get it equal to 0. If you can factor it, great. If you can't, use the quadratic formula. So it's going to be x squared minus 2x minus 8 equals 0. Any questions on how I got that? Okay, does that factor? What do you think? Two numbers that multiply to give you 8 and subtract to 2? Or negative? Yeah. So you're going to factor it in x and x. Your signs, yep, plus minus. Which one gets the plus? 2. And the minus is the 4. Looks good. So now what are my two answers for x? Negative 2 and 4. I'm not going to circle them yet because I got to make sure that neither answer causes me to take the square root of a negative. Let's check 4 first. What's 6 times 4? And then plus 12? That's a positive. So I'm not taking the square root of a negative. In fact, if you wanted to check it, what's the square root of 36? Just write that off to the side. So 6 minus, what's 4 times 4? Plus 9? Yep, and what's the square root of 25, which we can do? 5. And if you do 6 minus 5, do you get 1? Yeah, so that answer's perfect. Okay, so this one works. Let's check negative 2. What's 6 times negative 2? Let's check it up here. 6 times negative 2. Plus 12? What's the square root of 0? 0. Minus 4 times negative 2 plus 9. What's the square root of 1? 1. All right, so neither one of those causes me to take the square root of a negative.
0 minus 1.
But does it check? Question, Molly? Does it work? Yep. So it doesn't work, right? So even though it ended up, I didn't take the square root of a negative. That wasn't a problem. But when I checked it, it didn't work. So we have to make sure that something like this doesn't happen. And if it does, that's extraneous. Okay, so it can be a little more subtle to figure out that it's an extraneous answer if you don't check it carefully. Okay, questions on that one? All right, this one, even though it's cubed, it's not as bad because there's only a root on one side. So what would be my first step here? Cube each side. And I get x cubed minus 2x plus 2 equals x cubed. Now, we don't have a cubic formula, so we don't have an equation we can plug it into. So any other thoughts what I can try to do? What's one thing we at least like to do when you're trying to solve an equation algebraically with all your variables? Get them all on one side. So let's at least do that and see what happens. So just because I want x cubed to be positive, I'm going to do this the long way. I'm going to take everything on the left and put it on the right. Okay, just because I want x cubed positive. So that's going to give me x cubed minus x squared plus 2x minus 2. You don't have to do it this way. It's just the way I'm choosing to do it. And now you can factor here. Does anybody recognize what kind of factoring you can do? It's the kind of factoring you can do when you have 4 terms.
Group factor?
Yeah, you can factor by grouping. So take what you can out of the first 2, take what you can out of the last 2, and pray that when you do that, you're ended up with something that's the same. If it doesn't, then you're not solving this algebraically. So what can you factor out of the first 2? x squared. And what does that leave me with? So that's what we're hoping we get. What can you factor out of the second one? Positive 2. And what does that leave me with? Perfect. So now they both have in common an x minus 1. So factor that out. If you factor x minus 1 out of the first term, what does that leave you with? Just the x squared. Bring down your plus. And if you factor x minus 1 out of the second? 2. Now set each of those factors equal to 0 and solve them. 0 equals x minus 1. 0 equals x squared plus 2. Okay, what do I get for an answer? 1. Anything else? What about that other equation? It would be the square root of negative 2 as the answer. So what would that end up being? Yeah, it would be imaginary, so we can't solve that. All right, so in this case, that second equation didn't give you any extra answers. So the only answer is x equals 1, but I got to double check it and make sure that that doesn't cause me to either take the square root of a negative or some other weird thing happens. So let's check it. What's 1 squared? 1. 2 times 1? 2. Plus 2. Now let's do it out. What's 1 minus 2? Plus 2. And then the cube root of 1? 1 equals, and the number we plugged in was 1. So did that answer check? Yes. That's the only answer. Yeah. All right. So, okay, the last one we'll take a look at. This is an inequality. Inequalities with roots can be a little challenging, so we're going to stick with doing them graphically. And this is pretty straightforward. Take what's on the left in y1, what's on the right in y2. And then you're just going to take a look at where they cross, and you're going to look for the condition either where one is above the other or one is below. That's it. Okay, now I might have to adjust this to make sure they cross. Let me check it. 9 minus x squared. And x squared plus 1. So I'm looking for where the graph in blue is above or equal to the graph in red. Okay, that works fine. So notice this isn't our standard kind of looking odd index graph because you're squaring something. If you take that square out, then it would look normal. Okay, still some symmetry to it, but not quite what we're used to. All right, so now we're looking for where this graph is greater than or equal to the parabola. So I can see that that does happen. And what do I have to calculate on the calculator to figure that out? Yeah, I need 2 intersection points. So calculate the intercept. And I get negative 0.73, 1.5. Negative 0.73. What was it? We'll go 1.53. Did anybody find the other one? Okay. I'm going to assume it's symmetrical. It looks symmetrical, but if somebody can double check me on that just to make sure that it is symmetrical, that would be nice. And now while somebody's checking that, assuming that I am correct with that it's symmetrical, what would be the x values that satisfy this problem? Where is the blue graph above the red? Between what x values? Allie? And would you use a bracket or parenthesis on that? Bracket. Because we can equal. All right, did somebody double check that?
It is symmetrical.
It is? Perfect, thank you. Okay, if they wanted to know the opposite, where is the blue graph below the red? I would say from negative infinity to negative 0.75, and then from 0.75 on to infinity. Okay, so radical functions, not too bad to graph or even to solve as equations. Little time consuming depending on how many radicals are in the equation, but you'll never have more than 2. All right, so homework tonight on 255. Okay, so it's 1, 3, 5, 6, 12 to 14, 20 to 22, and 28, 31, 35. Right, so we'll take a look at that tomorrow. That finishes up chapter 4. Okay, tomorrow we'll start exponential functions, which is chapter 5. And then on Wednesday we'll finish what we're going to do this week with logarithmic functions.